If you find yourself in a workplace where there is a steam generator, also known as a boiler, you are probably going to find that you're also going to have some responsibility for what's called an open feed water heater. And there's some important reasons for that. Now, on the shorter term, you are probably going to be assigned a Rankine cycle analysis where an open feed water heater is added to the Rankine cycle in order to improve the thermal efficiency of the cycle. So I'd like to show you for either situation how to run through the computations associated with an open feed water heater. Okay, so on the short term, of course, I don't know who's assigning what in these classes, but a commonly assigned homework problem in Chapter 8 is a Rankine cycle, but an open feed water heater has been added. So let's go through some of the basics of this. Well, let's see. What's your basic Rankine cycle? You should know this by heart. The four major components of the Rankine cycle. And in many cases, in the real world, we're always trying to improve the thermal efficiency of our cycles. And an open feed water heater is one of those components where we can improve the thermal efficiency of our cycle. Let's see. You should also know, you should be pretty familiar with what the basic Rankine cycle looks like. And in the example I'm going to take you through, I'm going to say that the turbine is reversible and adiabatic, and the pumping processes are reversible and adiabatic as well. And so this is a sketch that I pulled out of the book, and I have beautified it a little bit. So this sketch is actually taken from the homework assignment you're probably going to have. And so let's see it. How is this different? How is this different from the basic Rankine cycle? Let's see. We've got a steam generator. That's the same. We do have a feed water pump. That's the same. But I see that we have something that's called pump one here. And I'll tell you the reason why we have to have that in a minute. Let's see, we've got a condenser. That would be common to both situations. I see that in the textbook, the author and the folks designing this power plant have divided the turbine up into two sections. Let's call it turbine one and turbine two. And so, of course, coming from the steam generator, we've got superheated vapor coming into turbine one, and it's going to be expanding isentropically to some intermediate pressure, not the condenser pressure. So do you see that it's this, what we call extraction point, is at a higher pressure than the condenser. And so this extraction point is very important to recognize. Do you see that it's a split in the piping? Some of the flow leaving turbine one is coming down to what's called an open feed water heater. The rest of the flow is going to turbine two, where we're going to make more power. And so we're going to expand the steam that comes into turbine two down to the condenser pressure, okay? And so we're going to have, well, not all the steam flow from the boiler, but a good proportion of the steam generator flow coming into the condenser. Remember that the condenser outlet is saturated liquid at a low pressure. Okay, now let's look at the added piece of equipment. It's called an open feed water heater. So let's see what that's all about. It's basically a vessel. More details in a minute. And you see, what we're going to do is we're going to say that in the sketch that you're provided in your textbook, it labels this Y and it doesn't explain it. So I'm going to try to explain what this Y means. Okay. It's related to this number one up here. Up here. Of course, this is state one, pardon me. So there is state one going into turbine one. Over here, the author has labeled this just one in parentheses. Well, one means that the mass flow rate leaving the steam generator is M, let's call it M dot one. So one represents M dot one divided by M dot one. Therefore, this little y in parentheses would represent M dot two divided by M dot one. So we've got a proportion of the steam generator flow going into the open feed water heater. you're going to need to be able, you're going to quantify what that is. Okay, and so this amount 1 minus Y, that's the remainder proportion going to the condenser where heat is rejected. So do you see that this open feed water heater, it's just a vessel, it's a cylindrical vessel. And so it's operating at a pressure P2. And what's coming out of this open feed water heater is going to be saturated liquid. So you're going to figure out exactly the amount of steam that is needed to heat up this water that's being pumped from the condenser into the open feed water heater at P2 to exactly obtain saturated liquid, leaving the open heater at state 6. So the reason you need pump 1, in addition to the original feed water heater, is you've got to get the liquid pumped up to a higher pressure from state 4, condenser outlet, up to state 5, open feed water heater inlet. Okay, and another thing I've done on the textbook sketch is I have moved the drain line from the side of the open feed water heater. I'm going to guess that whoever drew this sketch in the textbook didn't have much operational experience, because the outlet from an open feed water heater is always from the bottom of the tank. So I've redrawn the textbook sketch a little bit. So there's my state 6, not coming out the side of the feed water heater. So I got a kick out of that. Okay, I hope that I've explained. My purpose for going through that long explanation on that slide is to explain what's this Y all about, and what's this 1 minus Y all about. It relates to this parentheses 1 here. That's like 100% of the boiler flow. This is a common analysis. This is not tricky. We're not trying to be tricky, trick you up and confuse you. This is normal engineering analysis approach. Some notes about the open feed water heater. So do recognize we've got steam, extraction steam coming from the turbine at state 2. We've got water supply coming in from pump 1, called the condensate pump, at state 5. And steam, these two streams are mixed together. They're intimately mixed together. And we've got just the right amount of steam coming in to heat up, just amount of steam coming in to heat up this feed water, so that the vessel operates at a saturated condition, so that what's coming out the bottom of this tank is a saturated liquid. And so you will be in the real world, with a sight glass on the tank, you're going to be able to see a liquid level where above the liquid level is saturated vapor, below the liquid level is saturated liquid. A benefit for adding this device, in addition to improving the thermal efficiency, is that when you raise water up to its boiling point, no matter what the pressure is, when you raise it up to the boiling point, that results in dissolved oxygen, dissolved air, being removed from the feed water, and that's very good and healthy for the boiler, so that you don't have any possibility of rusting of the steel piping inside the boiler. And so that's really very important from an operational standpoint. That's why you see this open feed water heater equipment all the time in boiler houses. Okay, so that's enough physical details of the equipment. Oh, also, open feed water heater for our model is going to be fully insulated from the surroundings. So we've got a big jacket of insulation fully surrounding this cylindrical vessel. So we're going to say Q dot is 0. Okay, recognize that M dot 6, here's the statement of the continuity equation. M dot 6, what's coming out of the tank, must exactly equal what's coming into the tank, M dot 2 plus M dot 5, because we're operating steady state, steady flow, 2 inlets and 1 outlet. Well, what's our TS diagram going to look like? It's going to be more complex than the traditional Rankine cycle. You see something in common, right? So here's the steam generator process. We're heating up to superheated vapor. We're going through turbine 1 down to state 2, a lower pressure. This is where we're extracting steam and we're sending it to the open heater. We're also going into turbine 2. For your homework problem, turbine 1 and turbine 2 will both be isentropic. Whew, that's good. That's handy. All right. So we're coming down to state 3 at that low pressure. we're condensing the steam to state 4, saturated liquid, and then we're going into pump 1, called the condensate pump, and we're simply increasing the pressure only up to P5, to state 5, which is the pressure of the open feed water heater. So state 5 is going into the open feed water heater. Okay. What's coming out of the open feed water heater is state 6. That is a saturated liquid. Well, where does it go from there? It goes to the inlet of the feed water pump. So 6 to 7 is our feed water pump, in other words, pump 2, and then off we go to the steam generator. So I'm unapologetic. Our TS diagram for this situation is more complex than the Rankine cycle. So try to get some familiarity. If you take a screenshot of this and simply redraw it, that's okay. Just try to study on why is it that you're copying what you're copying. Let's go through some mass flow rate details. Let's look at the continuity equation for our open feed water heater. Okay, a little bit of a repeat, but this is so important, it's valuable to go through this again. We've got m.1 coming from the steam generator coming into turbine 1. At point 2, at state 2, the flow splits. So m.1 splits into two things. It splits into m.2, which is going into the open feed water heater, and what's left is going into turbine 2. And so that's going to be m.3. So look with your eyes. Here's going to be m.3 going into turbine 2. So do you see that? Turbine 2, one inlet, one outlet, steady state, steady flow. So this point that I'm wiggling my cursor around must be m.3. And so here's what I want to suggest is that m.3 over m.1 is going to equal to 1 minus y. Here's m.3 going to the condenser. Here's m.1 coming from the steam generator. So visually, I'm trying to show you that m.3 going into the condenser divided by m.1, leaving the boiler, is equal to 1 minus y, where y is some proportion. Well, and here's the proportion, y. So y is m.2 divided by m.1. It's going to be very elegant. So you say, oh, I'm getting confused. You're going to be able to elegantly reduce this continuity equation, couple it with the first law, and get to the promised land on this. Okay, so let's see. One last thing to see on this slide. Steady state, steady flow continuity equation. Let's see. m.1 is going to have to equal m.2 plus m.3 because those are going to combine in the open feed water heater, okay, and then going to be shipped off to the boiler feed water pump. And so m.1 is equal to m.2 plus m.3. And I thought I would simply write those out to try to get you a little more comfortable with what's going on. Before we get to this complex slide, the continuity equation for the open feed water heater. I've already said some things about this. So recognize m.2, what's coming into the open feed water heater is equal to y, some number less than 1, times m.1. That's the extraction steam fraction. Over here, what's coming into the condenser? m.3. That equals 1 minus y times m minus 1. Okay. Well, what's coming out of the condenser? m.3 equals m.4. Okay, fair enough. Okay. And let's see, the pump 1. m.4 equals m.5. Got it. Okay. All right. Well, m.5 must be what's coming through this stream. So I simply look up here visually and see that m.5 is 1 minus y times m.1. So I'm visually looking at my sketch. No way you can do this without a sketch. All right. So at least I've got an expression for what's going into the open feed water heater from compressed liquid from the pump 1. I've also got an expression for what's extraction steam that's coming into the open heater. And let's see, by the continuity equation, what would m.6 be? That's simply going to be m.5 plus m.2. Well, that equals m.1. All right. So m.6 must exactly equal m dot 1 because we're going back to the steam generator. So m dot 6 equals m dot 7 equals m dot 1. When you go through this for the first time, it does not hurt to write down all of these little continuity equations. Do whatever you want to do. Now, when you say, okay, I'm going to have to perform a first law analysis on the open feedwater heater, so I've got to plan my work. And so if you think about the open feedwater heater, well, here it is. Well, here. You see that you need H5. You're going to need H5. Let me go backwards. You see that if you're going to analyze the open feedwater heater, you need H5. That means that you've got to study pump 1 before you study the open feedwater heater. So how are you going to do that? So you need H5. How are you going to get that? Well, pump 1, let's see. Little w of pump 1, w dot over m dot, is simply going to be for the incompressible reversible pump. It's going to be V4 times P4 minus P5. You're going to know all those. Well, you'll have to figure out what V4 is. Well, you know the condenser pressure. You know it's a saturated liquid, so you can look up V4, and you're going to have P4 and P5. So you can get a number for W dot over M dot, the reversible work for pump 1. Get a number for that. Well, how about write the first law for this adiabatic pump? So let's see, Qn, 0, minus W out of the pump equals H5 minus H4. So you can show that H5 is simply going to be H4 minus W of pump 1. So it's going to be a bigger number. H5 is going to be a bigger number than H4 that you looked up. So get good with your units. So don't forget your units. In SI, going to be kilojoules per kilogram. In English units, the work of the pump, W dot over M dot's got to be in BTUs per pound mass. Okay, we're making progress. We're now going to apply the first law to the open feedwater heater, and that's going to enable us to solve for this y, this dimensionless number y, that's a number less than 1. So we're going to just draw a separate sketch. Here's our open feedwater heater. Coming in here at state 2, m dot 2 is y times m dot 1. Coming into state 5, the water from the pump 1. M dot 5 is 1 minus y times m minus 1. Okay. Well, what's coming out? Well, m dot 6 is simply the sum of those two, and you can do the algebra to see that m dot 6 is m dot 1 because ultimately it's got to head to the boiler, which is m dot 1. All right, so there's a better sketch. Let's apply the first law now for our sketch. 2 inlets and 1 outlet, steady state, steady flow. Is the open feedwater heater lifting a weight? Is a shaft coming out? No to either. Fully insulated. The vessel is fully insulated. So Q dot in is 0, W dot out is 0. So the left-hand side 0 equals the sum of the mass flows leaving. Well, that's m dot 6 times H6 minus the sum of the mass flows in HN. M dot 2 H2 and m dot 5 H5. Of course, changes in potential and kinetic energy we're saying are 0. Now let's see, if we divide all of these terms by m dot 1 and recognize that m dot 1 exactly equals m dot 6, okay, you can show that. So if you make your substitutions here, which I have not done, you can show that 0 equals H6 minus y times H2 plus 1 minus y times H5. Wow. Okay. Now, this isn't a formula. Don't blindly write this. This is not just a formula you get out of the book. This is a derived statement of the first law for the open feedwater heater, not a formula. Okay. So have I shown you that you've got one equation or one unknown? You say, wow, I'm still confused. I see y, but I see all these h values. Let's look a little bit more at these h values. H6. Here's H6. Well, that's simply H sub F. Okay. It's a saturated liquid, so it's H sub F at the operating pressure of this open feedwater heater, which is simply P2. Okay. What's H2? Well, that came from your turbine 1 analysis. You will have analyzed turbine 1 before you started in on this. Okay. Using isentropic analysis. S2 equals S1 for the reversible adiabatic turbine 1. What's H5? That just came from your pump 1 analysis that I showed you how to do. So that's going to be a key of finding H5. Okay, so I hope that helps. Hope that helps you see the procedure you've got to go through to get to the promised land to determine why. Once you have why, you have all the mass flow rates for all the components. And so this is a repeat screenshot of what a real power plant scale open feedwater heater looks like. You see the person standing on the ground. These things can be huge. The 3 inlets are inlet feedwater. That would be from your pump 1 and steam. That's the extraction steam. And then on the industrial side, there may be some situations where condensate from other parts of the plant are returning to this vessel in order to be raised to the boiling point to get undissolvable or uncondensable vapors out of the H2O. Wow, so I blundered through that. So the beauty of this open feedwater heater is to get the water back up to the boiling point at that pressure, at that operating pressure of the heater, in order to remove dissolved oxygen, which really leads to terrible corrosion problems within the boiler. And another thing is just recognize that what's coming out of this tank is saturated liquid, just sort of by observation, saturated liquid. Well, I didn't go through detailed numbers, but I sure do hope that this video has helped you better understand how to incorporate an open feedwater heater in your analysis of a system operating in a cycle, and or how you would incorporate an open feedwater heater into any type of boiler operation. Okay, hope that helps. And I think the next video has to do with reheating of steam.